Okay, so there are times when you will be asked to solve an equation like these where your unknown x is actually in the power. It's part of the power, or it is the power itself. These are called exponentials, and you need to approach them in a different way than you would to linear equations or other equations. Let's have a look at this one first. We've got 2 raised to the power of 2x equals 32. How would we approach that? Well, the key to these is usually to put both sides of the equation into the same base, because then you have something that you can compare. So in order to do that, you need to be quite familiar with powers of simple numbers. Notice therefore that 32 is itself a power of 2. It is 2 to the power of 5. 2 times 2 times 2 times 2 times 2. So if we write that as 2 to the 5, we've now got 2 to the power of 2x equals 2 to the power of 5. We've now got something that we can compare much more easily. Because if we're raising the power of 2 to 2x and it's equal to raising the power of 2 to 5, well, we can also say then that 2x equals 5, because our powers must be the same. 2x equals 5, we divide through by 2 to give us our answer that x equals 5 over 2, or 2.5. Okay, let's have a look at this one. 4 to the power of x equals 1. Now we're going to approach this slightly differently. We're not going to put these into the same base. This one relies on recognition of the fact that we looked at in a previous video, that anything raised to the power of 0 equals 1. So the only thing that we could raise any number to equal 1 is to the power of 0. Therefore, we know that x equals 0. Okay, finally, looking at this last example, we're going to use a similar approach to the first one. We need to get both sides of this equation into a form where they're both in the same base. So again, we need to recognise that both of these numbers are powers of 2. 8 is 2 cubed. So we'll rewrite the left-hand side as 2 cubed, 8, all to the power of x. And that equals 4. 4, of course, is 2 squared. So we've got down to both sides being to the power in base 2, but we still can't quite do a comparison of the indices like we did over here, because we've got this going on, this bracket. But if you remember from a previous video, when we raise a power to another power, 2 to the power of 3, all to the power of x, we multiply the powers. So we can rewrite this again. 2 to the power of 3x equals 2 to the power of 2. So we get, if we compare our powers, 3x equals 2, x equals 2/3, 2 over 3. Now you might have actually got that, by inspection or just by recognising actually that if we were to take, and we can use this as a check, that if we were to look at 8 to the power of 2/3, if you remember from when we looked up fractional indices, the denominator, the 3, shows that we're looking at the cube root of 8 squared. The cube root of 8 we know is 2, and 2 squared equals 4, which you could use as a check, or you might have actually spotted it in that way in the first place.
Okay, Mary, so let's have a look at this one. So solve x plus 2x equals 12. So what do you think you do first?
Okay, well, I want x on its own, so I would put x equals 12 minus 2x.
Okay, so a lot of the time we want to get x by itself, but what we want to do first is get all of these x's together. So can you see anything we can do with this? Get all these together in one place.
Oh, okay, it's 3x, isn't it?
Yeah,
so
absolutely.
3x equals 12. Oh, and so x equals 4.
Brilliant, spot on, well done.